Hi everyone, thanks for watching this video. Welcome to the channel Learn in Depth. So myself is Anand. I am a embedded system engineer. I'm just motivated to share my knowledge and learnings, whatever I'm doing, to the people who are watching currently and who are interested in to dive into the embedded field and who are the professionals who wants to just revise those concepts, whatever already they have learned. Yeah. So what we are going to learn today is how to write a program. So we just write a simple program and that converts into the process. How do we convert into process? When I say process, how it does. Okay, and then we learn in a program how to create a one more process. We call it as child process. How to create a child process. So those two things today we'll be learning. And how here is the first program called process main thread. Okay, so we have initialized some global variables and uninitialized global variables, and local initialized variables and local uninitialized variables. So the main intention of this program is like, so the program in you write, it gets converted as a part of binary, and it converts into the binary. Okay, it will have some sections, right? So when you say the program, will have text section. So this code, whatever it is there, will convert into text section, and we have a data section. So this all goes .pss section. We call it as global uninitialized variables, goes into the dot section. So which means this is a global. Those are the global variables, but it is not uninitialized. So those are goes into the uninitialized global variables. It enters into the .bss section. And local variables, so whenever the stack creates, okay, when the function goes executes, the stack's size will be created, and stack will have this local and uninitialized local variables. So when I say stack, what happens, it just assigns the creates a stack and starts executing. So those variable values might be a garbage value also, whoever the uninitialized value. When you comes into the global variable, what happens is the uninitialized values will be assigned to 0. It's a responsibility of the compiler to assign these values to 0. Okay, and those values will be printed out here, and I have used wait get char. So what happens is, just put the wait get char here. After printing those variable values, will explore the process. When I say the program converted into process, and we'll explore how this process control block will have. So whenever the process runs into the system, each process will have a process control block under the unique PID value. We call it as parent ID value. Sorry, we call it as process ID value. So GCC one, yeah, we have compiled this process. Okay, now what do we do is we execute this process. You guys can see now. So in a program we have, you see this, so we have a program. The global variable initialized 10, 20, 30 is as it is, and the uninitialized global variables, which is called as .pss section, will be assigned by the value zeros for that, right? So this is the responsibility of that. So what it does is not by the compiler, it does by the program. So when you see this address space of this variable or this many address, we have to initialize with 0. That is taken care by the starter code. Okay, and when it comes to the local initialized variable, so it's 40, 50, 60, the local variables are initialized as it is the value, assigned values. When it comes to uninitialized value, uninitialized local variable, that's what I meant here. So if you see by default LAU is byte, which means local initialized byte value. Assigned for 3, we didn't initialize anything, but the global variables uninitialized values are assigned to 0 defined values, but these variables are undefined values, which is there already in the stack region. So this might create a problem. Okay, so that's the reason it's preferable to initialize the local variable with some defined value to avoid the misleading or undefined behavior of the system. It looks simple, but when you create in a larger applications, or when it creates working in a larger environment of a program, so even this might cause some problem, because this uninitialized variable, right, it might keep changing. If you, let's say, now what I do is, you can take a look again. Let's running the program. You see this time 65. The behavior might change, right? But because of this behavior, it affects the process program of entire program. It doesn't have a proper check, or if you execute directly, this might create a problem. Okay, so now what happens is the program it's printed those information and wait for the get can. So now it executes. So what happens is now, so in other terminal, yeah, here's the other terminal. So what I do is create another terminal. You see this is the program. Okay, so this is the binary. This is, will be in the form of executable linkable format. If you see the command file, what happens is it shows that what type of file now it is. It's a ELF file, executable linkable format, and it's a 64-bit architecture for LSB shared object and x86 64 machine, 64-bit machine. Okay, and it's a dynamically linked everything basically. And what happens is here, now this file is a binary file, so ELF executable linkable format. So when I say this executable linkable format, which is there in the flash, assume now it is there in the flash. When you try to execute a program, dot basically dot slash the process name, what happens is the program which is there, okay, the memory management will picks the program we call it as job, which will put into the job queue initially from the job queue, and it just moved to the RAM. Which it moved to the RAM, we call it as a new process. It comes into a new process, and once the main resources or everything is available, and it moves to the ready state. So ready state wait for CPU to assign and it shall execute. Okay, so once it is in the ready state, what happens is whenever the CPU is available and all the resources are pinged for the process, it's ready, then it executes from the ready state to the running state. That's how this process will execute from the ready state to the running states. Okay, yeah, so whenever the process is created, we say this now the program, whatever we wrote for in the .c, right, in the .c format, it .c for this, if you see, yeah, this is the .c, that will be converted into the process, which means it is execution. So when you say process, this program under execution, we call it as a process. So that's how it's happening now. The program is under execution now, and it holds and it waits for the keyboard input, right? It waits for keyboard input. So whenever the process is in execution, that you can see that the process management, it creates a process control block to manage this particular process. So it creates a process control block, okay, to manage this particular process. So we have some concepts for context switch, so we'll come to this later to understand why this process control block is needed. Okay, now what we learned is we have written a program and we converted into the binary executable linkable format, and to see that we have a file, it's a command by the binary, it shows it should be in an executable linkable format. So how it loads basically is the OS ELF loader, it looks into the ELF file program header. So program header is the one which has the information where to load which section. So which means like we have a text section, we have a data section, we have a other debugging sections, all those sections where to load in the RAM. So from virtual address, it provides a virtual address as well. Okay, from the ELF. So when you do read ELF on to the binary, if you see read ELF, we have to provide some header information. So if you see the header -h, it shows the header information. So if you see, this is the ELF header, how it manages. Okay, and we know something, if you want to see symbols, it shows these are the symbols we have in our program. And if you see, this is the values, but we have another program header, file header, -a, it shows all. Okay, let's go to the help. If you see a, it shows all. Yeah, this is what we're looking for. Okay, here if you see, okay, program header, see we saying load, okay, which says virtual address offset of this should be the virtual address. All those informations will be provided here. If you go over here, section headers we have. So when you say section headers, we have the dot data sections, we have dot bss sections, and it's created 10 bytes because we created a uint32 short. Okay, and yeah, short also it's kind of 4 bytes, and dot bss section. Oh, some all those information. So here you have key flags as well, what it means and what it indicates for that. Okay, yeah, the virtual address and the physical address will be defined by the memory management unit. Okay, so this is the sections and how many offsets and what is the byte informations will be placed in the elf file. Okay, so elf header, what it does, so the OS elf header, it extracts the informations of the elf header and it looks for the program header. Okay, this is the one, and it loads what are the required informations or what are the required sections needs to be loaded from this to the memory. So once it loads from this flash to the memory, okay, we call it as a process gets created. So from the memory management unit section from here, whenever I try to execute dot slash, it will move to the job queue, and from the job queue to the memory based upon the availability of the memory in the RAM, it just copied back to the memory now, which means the RAM. So when it moves into the RAM, we say from the new process when it becomes to the ready process. It's a new process arrives and it sees that all the memory consumption or all the memory requirements are met, then it will be in a ready state now. So once the CPU is available to execute this program, then it moves from the ready state to the running state. That's how this works. Okay. So moving to that, so now it's process executing, right? So CPU is available and this process is executing, and we need to know what are the process states they are available. Okay, so how do we learn that? So see, if you, what happens is I don't have this one. Yeah, I opened the paint to explain the states of the process. Okay, so what happens is we have a new state. First is the new. Okay, it's a new, and it's a ready state, ready. Okay, and it's a running states. So by common, these are the general states we have, and we have a wait state. Okay, and we have terminate states. So the process life will be terminated. Terminate. I think yeah, it's a bit difficult to draw here, but hope you guys are easy. It will be catchable. Okay, so these are the states. So okay, now let's go. So once the program in the flash, okay, which is in the flash, okay, and it's try to enter into the RAM. So because basically the program whatever you written in the the root, it just resides in the flash. So the program will start executed by the CPU, which is it should be in the RAM. Okay, the program should be in the RAM to execute. Okay, that's a processor concept that does what process does. Okay, okay, that's a concept. Okay, so what happens is here, once the program whatever you have converted into the binary format, which is of elf type, that will be copied into the RAM. We say that is a new state, the new process. Okay, it's a new, the process we moves from the initial stage to the new state. Okay, because the RAM is available. Once the RAM is available, I wait for the CPU. It wait for the CPU to utilize this process. So once the CPU time slice is available to execute from this process, which means there is a queue. We have a ready queue. The CPU manages the ready queue. It first in first out. So basis. So what other process comes like P1 process, P2 process, P3 process. So on it keeps waiting. So when our process comes in the first, okay, and the CPU is available to execute from this queue, it looks okay. This process is now it's ready, and it's everything resources are available, and you can proceed for execution. Then the process will move from ready state to the running state. So this is what now running state. So this is what now we are observing the process in running state here till in the running state. Now it says process will wait for user keyboard input. So I have mentioned that it's waiting for the keyboard input, right? So what happens is now process moved from running state to the wait state by means of what? IO events. Here it is waiting for IO event or the signals. We can wait for either signal also, we can wait. Okay, any wait we can do. So now currently it is waiting for the keyboard IO event for keyboard. Once the keyboard event is arrived, that process will be moved from wait state to the ready state back, which will be put into the queue again. And once the CPU is available and the process comes in the first entry, then it starts executing. Okay. And one more scenario, is there any interrupt happens, okay, during the keyboard event or something, that interrupt might happen whenever the key press happens, right? So that will be separate ASR functions will be there. During the time, what happens when your process is running and it is interrupted by some other interface, let's say like GPU interrupts or any sensor data available interrupts or something like that, what happens is the running process will move to directly to the ready state when it is interrupted, because it is not looking for anything, right? It just interrupted, it just preempted basically. So that's how it moves from the initial to ready state. So once the process is normally terminated, it goes to the terminate state. Okay, it's the end of the process, end of the life of the process. Okay, or even you can't terminate the process by sending signals. So how do we trigger signals? Like control C, control plus C, what happens is like terminate the process, right? So control C, terminate the process, or control C force terminations, control Z or suspend the process. Control Z, if you type it, suspends the process temporarily. And if you want to resume, if you want to know what are the processes in the suspend state, if you can do jobs, when you type a command jobs, it shows in the current terminal what are the processes are in suspended. Okay, and then if you make it to run back again, resume the process, you can do like FG. FG is program process, so it just brings the process program and starts running. Okay, this is the process state diagram we have. Okay, okay, now what happens is, okay, now currently the process is in waiting state. Okay, now I have said that whenever the process is getting created, the process management is responsible to create a particular process control block for each process, right? So now let's explore, how do we explore that? So each process will create a process ID. So how do you check the process ID? Okay, so ps-eaf is the command which gives what are the process currently running, and the process you are looking as we have executed is 001 process main thread, right? So let's grep pipe tail of that. So it just show, yeah, you can see this is the process currently running now. Okay, so my process has the PID, process ID as this. Okay, so this is the process ID we need to look for. Okay, so now what you do is, so go for cat proc PID is 8865, go to the 865. Okay, so go cd first, we'll do cd. Okay, we have yeah, you see inside this process ID, this is created by virtual file system, so we can't create a folder or file inside this, because this is the virtual file system which creates the process ID for each process ID. Each process has a unique process ID, and this process ID will have those process control block informations. Okay, okay, so we'll not go to explore much details here, but what happens is like we'll see what are the things we are available. So if you see this CPU set, it has starting the root and mount stat and skim set stack. If you want to see the stack, cat stack, current stack, okay, with this permission denied. So sudo, if you do sudo, you see the stack. See what happens is now your process is waiting, right? It's waiting for entity y read, which means the keyboard read. It's looking for a wait. That's what's wait token. So it's wait whenever the key press happens, it token. Okay, so that's what it says. And cat status, if you see the cat status, you see the process state currently it's sleeping. Correct, it's wait sleeping, right? Because it is waiting for the input IO device event. Until that event comes, it is in the sleep state. So why do this process to run? That's what the state of the process is in sleep. And if you go virtual file systems also we have, so you can see the virtual file system in the maps. Okay, you can see this, right? So whatever we have explained, right? Here you can see these are the sections we have. uh, okay, so this is the stack section, 4K. So the page size of the is currently is configured as 4K. So this is read, write, execute, access, execute, and this section is last one is a either it is a private section, private to this process, or shared. If it is p mentioned, which means that this process whatever it executes at this region of the stack is private to this particular process at the space. It's not visible for the process or to access this. Okay, and these are the virtual addresses. The corresponding page maps or the physical address will be mapped by the responsibility. Okay, the size informations are here captured. You can see this is the stack, this is the heap region. Currently heap region is simply allocated for 4K, but it isn't used. Yeah. And shared library, we'll go over that part later. These are protected shared regions. Okay, and yeah, so the yeah. Okay, and then threads we have a read-only section, so constant variables. If you want it assigns this has a read-only section of this process, and read write is a global variable section, so global variable sections in a protected way. And these are the text section, so it is executable section. These are the libraries text sections access. Okay, but our process text section comes under this address space. This is read, execute. So these two things are read, execute things. Okay, fine. Now what happens? Let's say. Okay, so this is the process control blocks, uh, and we can explore more. Also cat fd, I think if you do this fd start cd fd, and let's if you do this 1012. So every process will have three file descriptors created by default. Okay, so when you say 0 is the standard input from the keyboard, and when you say 1 it's a standard output, and 2 is standard error. Okay, okay, so this is what the process control blocks created and how this variables looks like. And we have seen this initialized variables creates a problem in a local, so better to assign the value for the local variables to make your program benefit. Okay, so what happens is when I entered the key, process will be terminated. So when you try to look for again ls, it doesn't come anything because the process will be deleted. So the process will be deleted, so there is no PID for this uniquely. If you do cs and if you do proc, okay, if you do cls proc, yes, you see 8865. Did you notice anything? 8865, no, 886365 doesn't, because once the process is terminated, this process control block also will get terminated. Okay, yeah, thanks for watching this video. So what we learned today is like basically how to write a program, a simple C program, and how it compiles. Post compiling, how the OS will load the program into the memory, and how what are the states of the process we have, and how do we check the state of the process once the processes get created. The process management is responsible to create a process control blocks, and how to look the process by using the ps command with the process id. Okay, so those informations we have gone through, and few of the process control block informations we have looked. Okay, hope this helps and gain some knowledge over there. If you think that if you learn something new from this, please like and subscribe.